Good afternoon, one and all. My dear faculty members, Dr. Vishnu sir, and participants, a very good afternoon to one and all. Welcome to the final day of 6-day FTP on quantum algorithms and cryptography. All these days, it has been indeed an enriching week of learning, discussions, and knowledge sharing on the interesting domain. So over the past 5 days, we have explored the fascinating world of quantum computing and cryptography. So once again, welcome to this 6-day faculty development program on quantum computing, quantum algorithms and cryptography organized by Department of CSE A&ML, Keshav Memorial Institute of Technology. Now I will invite Ms. Vasanta to please introduce. Already it has been introduced and one session we have completed. So once again, if anyone who has joined newly, I request Vasanta ma'am to please introduce our resource person, Dr. Vishnu Srinivasa Murthy.
Good afternoon, everyone. It gives me immense pleasure to welcome you all to the final day of the AICTE Atal Online Faculty Development Program on Quantum Algorithms and Cryptography. As we gather for this afternoon session, it is my privilege to introduce our eminent speaker, Dr. Vishnu Srinivasa Murthy sir from Manipal Institute of Technology, Bengaluru. Sir is currently serving as an associate professor in School of Computer Engineering at MIT Bengaluru since August 2023. As many of you may know, Mahipal Institute of Technology enjoys the recognition of Institute of Eminence by the Government of India, holds a proud NIRF ranking of 6, and features in the 601 to 800 band in Times Higher Education The Rankings. Sir has had an academic and professional journey. Prior to his current role, he contributed at VIT Velluru, NITK Surathkal, Geetham University, ANITS, and GEC. Sir holds a PhD in music signal processing from NIT Surathkal under the supervision of Dr. Shashidhar G, along with a master's from Geetham University and bachelor's from GEC. Sir research contributions are highly impactful with over 55 publications in reputed journals and conferences, boasting an H index of 10. Notably, one of his works appeared in ACM Computing Surveys and another elsewhere per Expert Systems with Applications IF7 SCI indexed. Sir has also filed 2 patents, edited a book on malware analysis, and delivered more than 25 invented talks across areas such as IoT, speech and music signal processing, medical imaging, machine learning, and career guidance. Sir's passion for teaching and research has been recognized with the Best Teacher Award, and his dedication continues to inspire students and faculty alike. Today he will be speaking on the topic of immense significance in the area of quantum computing. As we all know, with the advent of quantum algorithms such as Shor's and Grover's, the security of conventional cryptographic system faces unprecedented threats. Post-quantum cryptography, therefore, emerges as a critical frontier, designing cryptographic solutions that remain secure even in the presence of powerful quantum computers. Dr. Vishnu sir will shed a light on the foundations, challenges, and the current research landscape in this crucial area. So, without further delay, let us warmly welcome Dr. Vishnu Srinivasa Murthy Yarlagadda sir to deliver his session on post-quantum cryptography. Sir, over to you, sir.
Thank you, Vasanta ma'am. To begin with, we will now move to our first session of the day. I request all participants to be attentive and make the most of this opportunity. Once again, welcome to KMIT Vishnu sir. Over to you.
Thank you so much, ma'am. Thank you so much. Thank you for. I think Madam itself had given the complete information about the post-quantum cryptography. So, ma'am, is it audible? My screen is.
Yes, sir. Yes, sir.
Ma'am, thank you so much for your detailed profile, brief profile about me. And so it's an afternoon session. I don't know how far I can do the justification, and this is a theory part. So last time it is a kind of practical session. I thought of covering it very nicely. So let me try to include some of the programs as well in this particular part as well. So my topic for today's session is introduction to post-quantum cryptography. So what is the problem with the existing classical cryptographic algorithms, and how post-quantum cryptography is useful when the quantum is established completely. That is the motive behind this particular session. So fine. It's a part of 6 days quantum 6 days online Atal FTP, quantum algorithms and cryptography. And congratulations to KMIT management of KMIT and Keshav Memorial Institute of Technology and Kishore sir and department of to the entire department of CSC ANML. So for organizing a well planned FDP on quantum algorithms and cryptography. Thank you so much. So I think these things I already discussed. I don't want to discuss again. So this today's presentation outline is mainly focusing on. So what is post quantum cryptography? So PQC stands for post quantum cryptography. So what is post quantum cryptography? And how Shor's algorithm and Grover's algorithm can overcome the problems of existing classical cryptographic algorithms. That means how they will create a problem to the existing classical cryptographic algorithms. So, for instance, RSA and AES. So, how easily they can find the prime factors, and as well as how easily they can search for the particular key. So, and all those things people might have explained during the previous sessions. Then quantum computing risk comparing with the climate, and that means climate changes in the world. So current security level, and we shall go with the NIST, that means National Institute of Standard Technology. Whenever we are talking about security algorithm, so it should be authorized by NIST, stands for National Institute for National Institute for Standards and Technology. So should I write it? Yeah. So then, what are the different types of post-quantum cryptographic algorithms are there? So then, what is the difference between quantum key generation and quantum key distribution, and what is the feature? So these are the outline of the presentation for this particular today's session. Since the topic is introduction to post-quantum cryptography, I have aligned with that, but I have aligned my topics with respect to PQC only. So quantum cryptography is cryptography for 21st century. So in 1900 and in the mid of 1900, classic computers have started the cryptographic algorithms, starting from Venom cipher, then basic cryptographic algorithms like DES, triple DES, AES. They had gone for the public key encryption algorithms like RSA, SHA, secure hash algorithm, MD5. MD5 is a part of that message digest. So these kind of variations you might have seen from the starting of mid 19th century. So, 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 These are the various algorithms have been invented, and at present, RSA is popular public as a public key cryptography. It is popularized. It could perform the encryption with the 1024 bits of key and 2048 bits of key and 4096 bits of key. Cracking 1024 bits of key will take months together, and cracking 2048 and 4096 will take years together. So this is the phenomena as of now. But, once quantum appears into the picture, then all these things can be done in days to hours to days. That means even 4096 key cryptography can be cracked in days. So that is a assumption as of now, since the quantum quantum machine has not been completely established. We don't know, but we are in the we can expect this kind of scenario in the next decade. The research is going to towards the quantum cryptography. So, on quantum machine establishment, fine. So, an importance and new feature of quantum cryptography is that the security of quantum cryptography protocols is based on the laws of nature of quantum physics. So, till now, we have seen the mathematics part of encryption. We used to have the zeros and ones. So, we used to apply some mathematical strategies and statistical techniques to perform the encryption and decryption process. But once quantum comes into picture, they are going to use the physics. So quantum physics is generally having the fundamental particles. So they are the parts of properties, we can say. But no, I'm saying that these are the particles. So to build the quantum machine, we need the protons, electrons, and neutrons. But to transfer the information through electromagnetic radiation, so through electromagnetic radiation, so we are using the photons. So these are the particles of quantum physics, and various elementary particles also exist in between, including noise also will be there. Till now we used to use the security, the communication channel, which will be built with the form of transferring the voltage, where the voltage is in the form of binary digits. So where binary digits can be cracked easily and can be viewed by the uh, eavesdropper. Yeah, so that is the um, scenario as of now. But once quantum comes into picture, then we are going to send the information through in the form of photons. So our binary information will be like this, either towards horizontal direction 0 or vertical direction 1. But now we are going to have the one more direction called as diagonal direction, which is called as a qubit. So in quantum, we are going to have the four different types of bits: one, zero, one, and plus and minus. That we have seen when I'm explaining the concept of quantum key distribution. Similarly, if there are multiple bits also there, the combination of 00, 01, 10, 11 also will be there. So in this case, we are going to use alpha 0 plus beta 1. So where alpha and beta are complex numbers, the square of the complex numbers will be equivalent to 1. So in this case, we are going to use alpha, beta, gamma, and zeta. Let us assume that eta or zeta, whatever it may be. So in this case, alpha square plus beta square plus gamma square plus zeta square is equivalent to 1. So likewise, uh, the things will happen once the quantum appears into picture. So we can consider the 0 and 1, or we can consider the combination of bits as a single digit. So that is also possible. We can use all the diagonals as well. So this diagonal information is nowhere is useful. So plus and minus will be considered as ignorant bits, and 0 and 1 will be considered as useful bits. When we are sending the information from sender to receiver, if there is a 0 and 1, we consider only those bits from the quantum, and those positions only will be considered from the key. So that process I already explained. If anyone want to explain me once again, then I'll explain the same thing. So as my is my flow fine, or everything is fine?
Yes, sir.
It's audible, right?
Yes, sir.
Yeah, because that day everyone has responded. I thought Saturday everyone will respond, but it's a post-lunch session. So I can understand the problem with the post-lunch session. Anyways, fine. So coming to the classical versus quantum information. In the classical information, we used to store, transmit, and process classical information in time and space. So the information will be always in the form of zeros and I'll take another ink since it is already black. Yeah. So it will be always in the form of zeros and ones. So the information is 0 and 1. 0 is nothing but ground, 1 is nothing but voltage. This is what we had studied. So if it is voltage is passed, then it is 1, and if ground is passed, then it is a 0 in the communication channel. So our entire data lies in between the ones and zeros till now. So, but the problem with the classical data is we can see the information of zeros and ones. If it is transmitting in the channel, we can tamper the voltages easily. That indicating that we can tamper the voltages easily from the communication channel at any point at any point, not only at the switch point or rotor point. We can extract the information from any point of the um, bridge. So but coming to the quantum information, as I said, that it is difficult to store, transmit, and process quantum information. We cannot store and keeps the things the problem. We cannot store and we cannot keep the things, but we can transmit the information. Transmission also will be done in the form of directions. That is for that photon directions. It will move from 0 to 90 degrees. That is a direction that we can see. Photons will always move in the communication channel. So, but however, there might exist some noise because the data is transmitted through the light. It's a kind of light transmission. So, but the problem is it is not possible to copy the quantum information because we don't know at what direction it is, how it is getting transmitted, and all those things. So, measurement of quantum information destroys it. So, that means the quantum information, if we measure it, and that means we can destroy the key and regenerate it. That is that we have seen. The same thing I have explained in the form of points. So classic computers information is always in the form of digital logic, zeros and ones representation. It's a binary representation using discrete binary values. Uh, so they are designed. That means we are going to design the circuits by using CMOS, semiconductor metal oxide semiconductor devices. So and always the information we used to see with the clock speed how much data will be transmitted uh, in second in second, how many operations can be performed in a second. So we used to see the throughput in the form of clock speed. So this is about the classical computers. But coming to the quantum computers, which was invented by Richard Feynman in 1980. So it's late years of 19th century, I can say. So fine. Now Richard Feynman, sorry, from 19th century, 20th century. So Richard Feynman has invented this uh, quantum computers. So exploits quantum theory and behavior of particles of at atomic and subatomic level. So this here we are going to use the qubits, quantum bits. We are not going to use classical ones and zeros. So can use two states and a superposition of the two states. That means we are going to use 1 and 0. We are going to encode this 1 and 0 in the form of plus and minus also. Um, the problem with quantum data is quantum effects will be there because some noise will be existing and uh, at the same time parallel operations also can be performed. So the data is 150x colder than normal space. data, and it is uh, very fast when compared to the classical computers. A typical quantum computer, how it looks like, a D-Wave 2000Q, the building blocks, it is having the QPU stands for quantum processing unit, not a CPU or GPU. Initial days, as I said that we used to have the processors in such a way that general 8086 processor, 8085 processor, which is of 8 bit, 8086 processor, which is of 16 bit, then 80186, 286. Oh, we used to call it as 80x86, 80x86, 80x86. And next, the Pentium P1 we had seen, P2 we had seen, P3 we had seen, P4 we had seen, then dual core processor we had seen, then Core 2 Duo processor we had seen, then we had gone for Intel i3, which is having 4 cores, then i5, i7, and now we are having i9 processor also. And we are having the Xeon processor with the multi-core system. And we are having the supercomputers nowadays with the multi-cores. So they will be called as GPUs. So we have moved from CPU to GPU. Then GPU to now we are moving to the QPU, stands for quantum processing unit. So quantum processing unit generally runs on an extremely isolated environment. It needs a separate environment. The physical enclosure is shielded by cryogenic refrigeration and shielded and IO system. So they will be called as refrigerated. They will be kept in the refrigerator and will be having the cubes, refrigerator cubes. We are going to keep inside that. So this is about the general architecture of quantum. So and the data will come. So from the controls of systems, so we are going to create the cryptogenic algorithms, cryptogenic circulation, and finally the data will be in the form of discrete ones and zeros. It will come, and we can transmit to the others. At the same time, we can transmit through quantum channel as well. So we are going to have one quantum channel, secured quantum channel to transmit the information when compared to the, it is secured when compared to the traditional or classical cryptographic algorithms. The same thing that I have specified. What is a quantum computer? They use quantum physics. As I said, that we are going to use photons from nowadays, not uh, whatever fiber optic cables and all those things, communications and all those things will not be so. So we are going to have a separate channel called as quantum channel. This quantum channel will be used to transmit the information. Apart from this quantum channel, we are going to use the regular channel, that is uh, insecure channel. We'll call it as, it will be always insecure. So this channel also will be useful. Now, as I said that instead of classic 0 and 1, they will use quantum bits. The quantum bits will be representing like this. 1 and minus. I already explained the truth table also. If the data is 0, 0, then we'll consider it as a bit 0. That means if the data is transmitted from the if the original data is, and we'll consider one Herman gate. So whenever based on the Herman gate, the output will change. So the output will be represented by psi. So it will be called as qubit. The qubit representation will be done by using the symbol called as psi. If it is 0, 1, we had seen already, it is positive. If it is 1, 0, it is 1. If it is 1, 1, it is negative. So this uh, truth table we have already seen, yeah, in the previous examples, in the previous session, sorry. So the so till now we are in assumptions only. We don't know what will happen if it comes to the reality. So that means the assumptions are saying that so the quantum computers, so the quantum transmission will be safer, and we are preparing all the algorithms for the future establishment, that means for the future established quantum machine. So it is about established. People are even uh, our states also, all the southern, all the Dravidian states, they have kept the tenders for the quantum environments, that is quantum, what we can say, to establish a quantum infrastructure in their own states. So everyone has is quoting nowadays. Even many institutes are putting tenders for establishing a quantum uh, laboratory. So it should not affect any this is one. Even Manipal, we are starting one quantum. So in another 1 year, we may establish the complete lab for the quantum computers. So if they are available, so they are exponentially faster when compared to the modern supercomputers. This is one another thing that we have to make it note. Yeah, ma'am already told there are two important algorithms. So I think they were discussed already in the previous sessions. I had seen the topics of the FTP. So in that, Shor's and Grover's algorithm have been mentioned. Apart from the quantum key distribution, so then you might have understood the importance of Shor's algorithm as well as importance of Grover's algorithm, where Shor's algorithm will be used to find the simplify the factoring problem. So generally, what will happen is nothing but if you have a larger number, finding the prime factors for this large number is the uh, key task in the case of RSA. And present whatever GNFS technique that they are using, so is computing the is designed to compute the prime factors, but it is little slower for to find the prime factor. Hence, we are assuming that this RSA algorithm is secured when compared to the other public key cryptographic algorithms, and we are saying that a 1024-bit key needs months to years to get cracked, and 2048 and 4096 will take years together. That means we are quoting that they need 100 years to get cracked by the eavesdropper. So, but once quantum computers are comes into picture, there is an algorithm called as Shor's algorithm designed especially for the quantum computers. This Shor's algorithm, if it is running in the quantum machine, then definitely it could crack the RSA 1024-bit key in hours. 2048 hours to days, and 4096 it needs at least a week. So the problem with the existing algorithm, RS algorithm, is if any data is already existed inside the cloud, and if you want to secure it, if you secure it with RSA, since it is taking months to, so they are going to use high bit code, that means large bit code, large bit key, sorry, not code, large bit key. So to keep it secure for hundreds of years. But once Shaw's algorithm comes, the existing information is no more safe. It can be cracked in hours to days. So the beauty of this particular algorithm is it can find the prime factors of large integers in less time when compared to the uh, classic computers that are currently available, classic supercomputers that are already available in the market. So it was designed by the Peter Shor. He is an American mathematician in 1994. So once it comes to the reality, there will be a serious threat to the algorithms like RSA, ECC, DP, so key exchange algorithms. So where they are generally where they are generally used to keep the information securely for the current scenario. So this is about the Shor's algorithm. Do you want me to run the code for RSA? Is it not required? If you want me to run the code for a simple RSA, then I'll run it. Do you want me to run? Can anyone respond?
Sir.
Okay, I'll run it then. Yeah, I'll run the simple code for RSA. If you want, you can use parallelly with me. That means if you have laptops and all those things, you can parallelly run the RSA algorithm also in your machines. So 1 second to do that, I'll upload my code in the cloud because it is in other machines. Uh, 1 second. One second. Sir, sir. Yeah, it is getting connected. Yeah, research.colab. Yeah. Anyways, I need not change the code. I'll run in this only directly. So collab research. Yeah. So this is the simple QKD, right? It is sorry. Yeah, fine. So here I have yeah. Here I have used two important simple packages. One is import random, and second one is from uh, a symbol pi import is prime. So this is prime function will be used to, is prime package will be used to know whether the given number is prime or not. Simply. Sir, is my voice audible?
Yes, sir.
Yeah, yeah.
Audible, sir.
You can parallelly run if you can parallelly do the things if you want. If you want me to share the code, I'll share it. Yeah. So this is about random and simple pi. The next function that I have used is simple one. Nothing. It will be used to generate the random integer from 100 to 999. I can generate it from the 1 to 100 also if I want. So what I will do is I will generate it from the 1 to 100. Yeah. Now I can print the generated number also if you want. So this code will be used to generate the random numbers. That is done. Next, we know the recursive function for the GCD. GCD will be used to find the GCD of two numbers. For instance, GCD of 108 and 30 is always 6. GCD of 48 and so everyone knows that how to find the GCD. I'll not put much effort, just but I will cover it. Simple slide. Yeah. Yeah. So GCD is nothing but suppose if 108 is equivalent to 30 into 3 plus 18. So 18 is not equal to 0. 30 equal to 18 into 1 plus 12. 12 is not equal to 0. 18 is equivalent to 12 into 1 plus 6, 6 is not equal to 0. So 12 is equivalent to 6 into 2 plus 0. So GCD of A comma B is always B equal to 0. So return A, else uh, uh, GCD of B comma A mod B. It will be recursively called return. So this is the simple GCD function that we used to see. So the same thing I had changed it to recursive function here. Define GCD of A comma B while B still till BCD B exists till B is not equal to 0. A comma B is equivalent to B comma A mod B. So it will be recursively called. So once B equal to 0, it will return A. The same code, it is done. Next, A inverse modem will be identified with this particular code. So using if M equal to 1, return 0, or if while A greater than 1, Q equal to A integer division M. So double slash is nothing but integer division. M comma M A is nothing but A mod M comma M. So it's a kind of GCD process. X naught X1 is equivalent to X1 minus Q into X naught and X naught. So this is the way of, if you want me to take example and explain, I'll explain this one also. So this is about mod inverse, A inverse modem. Yeah. The next main important thing is RSA encryption. So I don't know. The next main important thing is RSA encryption. So P
Charging
equal
is
to
Sorry to disturb. 18% charging is there. It may your device.
Ma'am. I think there is power issue. No issues, ma'am. I have laptop. Otherwise, I'll connect to laptop. Don't worry. Yeah, power came. No issues, ma'am. So I kept laptop as safety purpose also. Yeah. So P equal to generate prime number and Q equal to generate prime number. So it is going to generate two prime numbers within the range of 100 and 1 to 100. If you want me to generate in between 11 and 17, if you want to generate 11 and 17 also, it can be done. N equal to P into Q. 10 into, 11 and 7, 11 into 17, that is 185. P minus 1 into Q minus 1, that we had seen. The commonly used key value is 65,537. It is 536 plus 1. It is a highest value. That is 2 power 16 is equivalent to 65,536 plus 1 value we are considering here. While GCD of E comma phi equal to 1, E equal to random dot randint of 2 comma phi. So in that range from 2 to 5, we are going to generate the random number and we are going to check whether GCD of E comma phi equal to 1 or not. So this will be recursively done. Finally, D we are calculating by mod inverse of E comma phi. That is the inverse mod phi of n will be the D. So return E comma n comma D comma n. So we are going to generate the E comma n, which is for encryption, it is a public key. D comma n, where it is for decryption, it is a private key. So this is the process that will happen here. Yeah. Let me connect to laptop once because that will be easy for me. I can show the things also to you. If you want to do the coding along with me, you can do it. That's appreciated. What is the code? I thought of it will be easy for writing the things. That's why I connected.
Is it audible?
Yes, sir.
Yeah, fine. If there is a noise or disturbance, please let me know. Anyways, hope the screen is visible. Yeah. So this is import random and all these things. So this is already explained. Then yeah, define generate random prime number also it is done. So what will happen? I will explain here. If we call a define random number, so alt enter. Yeah. What will happen here in the sense? Suppose if I'm calling to generate random number, P is equivalent to generate random number. So generate prime number. Random number. So print P. So P value is 29. So but if I give up to 20 only, it will generate within 20. 19 is the prime number. That's good. Fine. So GCD of A comma B, it is going to find the GCD of two numbers. So for instance, if I give GCD of 108 comma 30, so GCD of 108 comma 30 is always 6, as I said that. So mod inverse of A comma M. So we know the private key the encryption key is 23 in case of 11 and 17 that we had seen there while we are performing that RSA operation. So if mod inverse of A comma M. Now if you give a mod inverse of 7 comma 1 phi of n, right? 160. It is going to give 23 as a key. That means if 7 is the encryption key, 23 will be the decryption key. So that we are finding by using the mod inverse operation. So then this is the RSA key generation. Now if you want to print the p value, so print p value is p print q value as q, n value as and phi of n is print phi of n is 5, and that's good. That is the beauty. Here we used to have some part of the code, right? Yeah, that is the, but while GCD of e comma phi equal to 1, we are going to calculate the e value. So print the e value as decryption key is D. Print D value is D. Now if we call the RSA, this RSA key generation, RSA key generation. So P value is 19. What is the P value? 19. Then 1, 4, 15, 16, 17. Q value is 17. 19 is to 17 is equivalent to 323. 18 into 16 is equivalent to 288. E value is 65537. I'll keep E value as 2 initially. Yeah, P value is 19, Q value is 17. Then E value is 5, D value is 173 in this case. So E mod, that means E inverse, 5 inverse 323, sorry, 288 is equivalent to 173. Now 5 under 323 is known to everyone, but 173 is known to only the person who can decrypt the information. So encrypt message is same. So power of that means character will be converted to integer. So and we are going to send e comma n for each and every character in the message. You can write the for loop like this. We are creating the list and we are going to encrypt the information for the list. So e power n, that means m power e mod n will be the encryption process. Power of m comma e mod n. So this is the encryption process, and the decryption process is power of ciphertext power d mod n will be the decryption process that we have seen everything. So here p value that they had taken is 3, q value is 5, very simple values. 3 into 5 is 15, where 5 of n is equivalent to 2 into 7, that is 2 into 4, that is 8. E value is 3 and D value is 3. If you run it again, you may get different values. 19 and the Q value is 2. Q value should be greater than 2. Is prime of number as well as and number must be greater than 2. Then only we have to return the key. So that we can write. So we can run this algorithm again. So P value is 13, Q value is 11. Perfect prime numbers, 11 and 13. So 11 into 13 is equivalent to 143, and 10 into 12 is equivalent to 120. So E value is 7 and the D value is 103. So D value lies in between 0 to 5 of n minus 1. So 19 power 7 mod n will be the encryption value. So encrypted message, where is that encrypted? Yeah, 19, 108, 54, 54, and 40. These are the encrypted value, encrypted message. It will be different characters compared to the hello. And decrypted message is hello only. That is 19 power 103 mod n mod 143. So fine. The number is 143. Very nice. So shall I share this code with you people? Is it fine? This one as well as quantum key distribution also I'm sharing.
Yes,
Just
sir, share.
practice it one. Yeah.
Okay, yes,
I
please
will
share, sir.
share it. If you want to practice now, I'll share it now itself. Otherwise, I'll share it through Kishore sir, because we have only half an hour left. That's why I have spent a lot of time on this actually. Yeah. 1 second. Let me come back to the shorts. Coming to the Grover's algorithm, I already explained about the AES algorithm in the previous session. So where the 128 message key will be encrypted by using 128-bit key. So while it will take 10 rounds of process for encrypting the key. For each and every round, the key will be modified, and whatever the key that is used for the 10th round will be given as a first round of decryption process that we had seen. But the key searching is quite difficult in the previous cases. But once this Grover's algorithm comes into picture with quantum machines, then it is very easy to crack that, easy to search that. So it won't take much time. So AES is also in danger. So whatever the classical cryptography algorithms that we had, starting from RSA, ECC, Diffie-Hellman, and Grover's AES and 3DS, asymmetric encryption algorithms. Apart from these things, whatever we are thinking that Bitcoin, that means light cryptographic algorithms in Bitcoin, whatever SHA algorithms and all those things, all the secured hash algorithms which could encrypt with 128-bit key also are in danger with the uh, quantum machines. So people are not understanding the risk with the quantum computing, where quantum computing risk is similar to the climate change. How the climate is getting changed, the same kind of scenario will be with the quantum computing. So they should be the both of them should be taken care of. So we have to take care of our climate conditions because of these industries and pollution and all those things. How the climate is getting changed. How the climate is getting, environment is getting spoiled rapidly. So the existing secured algorithms also will be cracked or will be under risk with the quantum computing. So this is so since the future is towards to the quantum computing or quantum machinery, so we have to understand the future impact and act now. So similarly, we have to take care about the climatic change, the climate situation, climate change as well. Yeah. So these things are already discussed. We have public key crypto systems as well as symmetric key encryption algorithms. So where public key crypto systems can be cracked easily with the Shaw's algorithm, where Shaw's algorithm is efficient to find the prime factors easily when compared to the existing GNFS approach. So even though the size of the key is increasing towards 4096, it can be cracked in uh, days to weeks. So that is a problem with the that is a issue that we have to face in future. Even elliptic cryptographic algorithms are all these are in danger. And coming to the symmetric cryptographic algorithms like DESR, triple DESR, AES algorithms are also in danger, as even 128 and 256-bit keys can be searched easily. So I think I'm clear with that. So the same thing has been kept in the form of diagram. So the public key cryptographic algorithms are in danger with the Shor's approaches.
where the symmetric cryptographic algorithms are in danger with the. Let me switch on the video as well. Sorry, I didn't. So the where the symmetric cryptographic algorithms are in danger with the AES and SHA-2. So not Grover's algorithm. So coming to the standard. So what the secured standard NIST is taking care. Actually, I'm using mobile hotspot. Is it okay, sir, if I switch off video?
Okay, sir.
Yeah. So let me take to the NIST the and as well as FIPS standard given for specifically for quantum cryptography. So I will take you to the NIST standard. First of all, I'll always try to show the reality first, then I'll come back to the, yeah. So we have one standard, hide video panel. Not anything. So NIST, National Institute for Standards and Technology. So it has released different approaches. So it has released one standard, three different standards in 2024. One is FIPS 203, FIPS 204, and FIPS 205. These three standards have been released by the NIST in 2024, mid of the 2024, that is in August of 2024. I hope I remember properly. So, and one new standardization technique had come called as Federal Information Processing Standard. So, from now onwards, FIPS standard will take care of uh, different mechanisms for securing the information through quantum machine. So, this FIPS 203 will be called as module lattice based key encapsulation mechanism standard. So, mathematics lattices you might have seen. So where lattices, 2D lattice and 3D lattice, I'll show you for simple, 2D lattice, how it looks like, and the 3D lattice. Yeah, if you see the 2D lattice, it will be looking like this. We have to transmit the information from one point to another point through these lines. So you might have seen these lattices in mathematics. So now, if you see the 3D lattice, the 3D lattice will be looking like this. I can show this one. Yeah. The 3D lattice representation will be looking like this. So with this 3D lattice, it is possible to generate the smallest possible key even for the quantum cryptography. That is what said by this FIPS 203 standard. So this is FIPS 203 standard. Will be using the lattice mechanism, and there are different types of algorithms like module lattice key encapsulation mechanism. So MLKEM. So there are different variations of MLKEM has been identified in 2024. MLKEM 512, MLKEM 768, and MLKEM 1024. And still there are some proposal calls for enhancing this particular variations. So this is about the FIPS 203. This is one standard. And coming to the another standard, FIPS 204. This FIPS 204 is a digital signature standard. So that is this is for establishing the. So previously we are using the digital signatures using uh, RSA on as of now RSA only. Secure session layer will start and digital signature will be created before certificate authority will be given before sending the information. Then after receiving the information, we'll check whether it is received from the same with the same signature or not. So that kind of verification we used to do as of now. But once quantum comes, we are going to create a lattice-based digital signature standard So that cannot be cracked by anyone. So because it will be transmitted in the quantum channel. And coming to the FIPS 205 standard, this is also hash based, stateless hash based digital signature standard. There are two approaches for the hash based technology. One is uh, state based hash, state known hash based digital signature standard, and second one is stateless. I'll show how that hierarchy will be there. Hashing hierarchy. I think I can show this keyword. Not with this. There'll be a bottom up approach. Very nicely, it will be designed. There'll be 8 blocks, A to H. Stateless. Otherwise, I'll give directly stateless hash based digital image. Yeah, this tree is any tree is fine. Yeah, this is perfect. So there are, as I said that, is it visible? Yeah. As I said that there are A, B, C, D, E, F, G, H. There are 8 states at the bottom level. So now A and B will be individually, all these 8 blocks are individually applied with the hash function HA, HB, HC, HD. So the outcome of those hash functions will be called as H2, HA to HH. Yeah, fine. So now the next level, the pairs of A and B will be that is the pairs of the hash outputs will be used considered. So HAB, HCD, HEF, and HGH. Then ABCD will be considered together. It will be HABCD, HEFGH, and ABCDEFGH. Finally, it will be ABCD. So one hash function. That means if you know, sorry. Yeah, fine. So one is we know the state where in which state we are and where we are performing this hash function. So that is the present scenario. But if you don't know the state and if you perform the digital standard and if you can automatically identify the state at the receiver side, see performing all these hash functions at higher level will be computationally expensive for the existing machinery or existing classical supercomputers, what I can say. But with the quantum computers, we can do these hashing and operations easily. And we can say that it is a stateless hash-based digital signature. So these 3 standards are currently released by the FIPS, stands for Federal Information Processing Standard. So which is designed by, that means which is introduced by NIST, stands for National Institute Standard Framework. So there are lot many calls for the various secured algorithms. There is a table also. I have seen one table as well in this particular site in detail. Yeah, post quantum cryptography standard call for proposals. Now there is from 2017 onwards they have started calling proposals. In 2018 they have received some few, and there are around 62 proposals they have received. And out of them, around 9 have been selected for FIPS 203. 3 have been selected for FIPS 204, and 2 have been selected for the FIPS 205. So there is a table. I missed somewhere. I'll share it with Kishore sir later once the session is over. So yeah. Yeah, this is about complete NIST. So that means if you want any algorithm that has to be developed for the quantum machinery, you can design a new approach for the lattice-based key generation algorithm or mm, key generation algorithm, or it can be for digital signature standard, or it can be for the hash stateless based hash FIPS 204 also. So this is about complete types of. Uh, there are three main types of post quantum cryptographic algorithms. One is code based, that means lattice code, and second one is hash based, and third one is signatures, that is digital signature standard types. So these are the three important types of post quantum. There are still some more types are existed, but they are not infogeneous there, and they are not coming to proper reality. So fine. So this ML3 hashing, I said, right? McEltree hashing. So that is the approach, taking 8 blocks and doing it stateless encryption. So fine. How post-quantum cryptography will be useful? The traditional cryptographic schemes will be based on the that means classic computers. So they are quantum resistant and obsolete for the quantum machinery. But once and completely based on the mathematical hotness, and we have to generate the keys and mathematical prime factorization, and all those things have to be done. And once Shor algorithms and Grover's algorithms, which was explained in the previous sessions by some of the experts, if they come into reality, then it is very easy to uh, crack that is crack them. It is very easy to crack them. When compared to once come to the quantum key distribution, so which we already discussed. Should I just go of it once again, or not required? I think fine. So quantum key distribution. So where previously the communication channel will be filled with the zeros and ones only, but now we are having 0, 1, and diagonal information plus and minus also. So I have explained with the complete process. I'll just give a glimpse of it in the 10 minutes. Don't worry. As I said that. So once post-quantum cryptography comes into picture, then it will be kind of hash-based. So that is Merkle signatures and strings and the stateless signatures. So that Merkle signatures are nothing but it's stateless hash-based signature. And next one is code-based. It is completely lattice-based on the lattice code or whatever Merkle is code. And the multivariate quadratic functions that can be done, and lattice based there are different approaches are available as of now, and isogenes is another approach. Isogenes, it's the super singular elliptic curve cryptography, that means it's advanced to the TCC. So all these algorithms are safe from Shor and Grover's algorithms also, because Shor and Grover's algorithms can identify the search the data and all those things. Even though quantum machinery is there, it can be search the information in the insecure channel. That means that's a current channel which is with the zeros and ones. So once quantum comes, we will be transmitting the information to quantum channel. Yeah. Post quantum asymmetric crypto algorithms. So coming to the factorization. Um, Lattice-based cryptography and then the multivariate cryptography. These are the two techniques. In lattice-based cryptography, already presently two some algorithms have been designed. One is learning with errors. So that is one important thing that we have to remember. And coming to the asymmetric. So in this case also we have symmetric and asymmetric approaches. Where symmetric will be in symmetric case we are going to use the same key for the both receiver and sender side. Coming to the asymmetric side, asymmetric cryptographic algorithms, we are going to use the two different keys. One is public key and private key, where public key is known to everyone, and private. So anyone can encrypt the information with the public key of the so and so person, but only the private key, the one. Suppose if I'm sending it to some B, A to B. So B, if he is having the private key with respect to his public key, then only he can decrypt the information. That is the beauty of public key cryptographic algorithms. That same approach will be followed even in post quantum systems. So yeah, these are the some approaches that are already available in the implementation, already implemented. known PQC implementations we can see. So these are already implemented. Lattice based, super singular AC, isogeny, or code based, multivariate based, or hash based. These are 5 different approaches uh, provided by the based on the NIST standard. As I said, that sorry, I forgot that I included in the PPT. So based on the NIST standards, so these are the 5 different approaches. So I think these things are required. So what I will do is I'll explain that glimpse of QK concept just so that I can wind up the session. Yeah. So before going to a glimpse of KD, one important thing what people have observed is if you go with the quantum channel completely, we don't know if noise exists in the sense. Quantum data cannot be tampered as it is in the form of photons and it will be always rotating in the channel. So no one can identify the direction of it. But coming to the noise, once if noise exists, we don't know whether we can get the information properly or not. As in QKD also, I explained about the importance of transmitting the information in uh, through insecure channel also. So in future, if we can use news approaches instead of SSL, as of now we are using secure session layer. If we can introduce one more terminology like quantum safe component, TLS session key, then which is a hybrid of existing classical cryptography as well as upcoming quantum cryptography. If we can use the hybrid approach along with the uh, quantum, so then we can secure the information uh, to the more extent. So still there are open source projects are open quantum projects are available in open quantum safe. So this is as of now it is one of the open quantum safe project. There are many open calls that should provide that they're expecting the proposals for security with respect to quantum machinery or for image processing approaches with respect to quantum machinery, how we can design new how we can improve the algorithms and all those things with respect to quantum machinery. There are a lot many open calls are there. All these things with respect to security, we can always look into that NIST. And with respect to other approaches for the quantum machinery, so we can always see other proposal calls also. If anyone is interested to make a quantum machine, then if they are good at physics and if they can design such kind of quantum machines, for them also there are open calls for submitting the proposals. So I'll go to other device. 1 minute, just only 1 minute.
Sir, we are unable to hear you, sir.
Now, ma'am.
Yes, sir. Now audible.
Sorry. Yeah. 001101101001. So just I have told that these are the bits 0 and 1. These are the bases 0 and 1. If 0 and 0 is there, with Harman gate it will be 0. 0 and 1 will be there, it is plus. 1 0 it will be 1 and 1 1 it will be minus. So 1 2 3 4 5 6 7 8 9 10 11. 11 bits are taken. So 11 is my lucky number, let's assume that. Then these are the original LIS bits or source bits. He will be having basis. The basis can be anything. It can be 1 1 0 1 0 1 1 0 0 1 1. Let us assume that this is the basis. Accordingly, we are going to generate the qubits. Yeah. Accordingly, we are going to generate the qubits. I can draw this diagram very nice. Yeah, this is very easy to draw in iPad. Fine. 0 1 is nothing but it will be. Then I'll do one thing. I'll remember this data. 0 0 1 1 0.
sorry, 00110101010101. Let us assume that this is the data. Sorry. Yeah. So take this. This is alias bits, alias bases. These are the qubits generated. Let us assume that, and Bob basis. And Bob bits. And these are Bob bases. And these are alias bases. These are qubits. Now I'm going to create some 11 bits. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let us assume that it is not allowing more than 9. So take a 0, 0, 1, 1, 0, 1, 1, 0, 1, and 1, 0, 1, 1, 1, 0, 1. Then 0, 1, 1. Let us assume that all these are random. 0, 0, 1, 1, 0, 1, 0, 1. Let us assume that all these are randoms. 0, 1. What is the value? 0, 1 is nothing but it is positive. Then the qubits I'm keeping in red color. Then 0, 0, it is 0. 1, 1, it is negative. Then 1, 1, 1, it is negative. Then 0, 1, it is positive. Then 1, 0, it is 1. 1, 1, negative. 0, 0, 0. 1, 1, negative. So I had told one more truth table. If you remember, on that day, it's easy. If you remember the truth table, it will be easy. A, B, and B dash. That is Bob basis. Then psi dash will be 0, 0, 0. Now we are having 3 bits: 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Psi dash will be, yeah, 0, 0, 0. It will be 0 only. 0, 0, 1. It will be 0 and positive. Then 0, 1, 0. Positive and 0. That is positive. Then positive and 0, 1, 1. It is a positive and 1. It will be, what will happen? Hmm, 1 second. Let me see that truth table I remember. 1, 1 is negative. 0, 1 is positive. Positive and 1 will be 1 only. It must be 1. Sorry, it must be 0, because as I said that day I had told one more information. If B and B dash are same, then A will come as this. So you can remember that logic. It will be 0 only. 1, 0, 0, it will be 1. 1, 0, 1, it is negative. 1, 1, 0, it is negative. 1, 1, 1, it is 1. So this truth table also, if you remember, it is easy. Just you need not remember this truth table. By understanding, we can say that. But to fill the values, it will be easy. 0, 1, 1. 0, 1, 1 is nothing but it is 0 only, because B and B dash are same. Then 0, 0, 0, it is 0. 1, 1, 0. 1, 1, 0 is nothing but it is negative. Then 1, 1, 1, it is 1. Then 0, 1, 1, then it is 0. Then 1, 0, 0, then it is 1. Then 1, 1, 1, 1. Then 0, 0, 0, then it is 0. 1, 1, 1, then it is 1. Yeah. So now, yeah, and now what I'm telling, I can tell in our phone. I can, as a Bob, I can call to Alice and say that keep the information off. What are the same bits B and B dash? This one is on. this one is on, this one is no, and this one is on, this one is on. S, 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 S. So keep these bits and ignore the remaining bits. I can say like that. So what is the bit that is ignored here? Consider the bits of remaining all those things, ignore the third bit. So I can call over the phone to Alice and say that these are my bit positions. I can give a challenge to the eavesdropper. If possible, crack it. The eavesdropper cannot do anything. So in this case, Bob's key and Alice key both are same 00101101. This is the Bob's key and this is the Alex key. But to verify whether it is damaged through the quantum noise or not, what I can do is half of the bits also I can say 0010 are my first four bits. Are they matching with you? If they are matching with you, fine, proceed. If they are not matching, then I can say that there exists a eavesdropper in between. I can say that the channel is not safe. So this is one important key distribution algorithm in the upcoming post-quantum. Once the post-quantum cryptography has started, we have to start our process with this particular QKD only. So this is one of the important thing. So I think I have covered completely, sir.
Okay, sir. Okay.
So thank you. Thank you so much, sir. Kishore, sir. Now it is open for the questions.
Sir, I have a question here
Please,
on the
please.
screen only.
Yeah, ma'am.
No, before that one, where you were showing, this one.
Hmm.
Not this one, sir. The calculation one, where you were showing us the window. Now, after doing all these things, we are telling over phone what are the bits to be considered and which bits are to be neglected, right?
Yes, yes.
Is it, I mean, if at all the number of qubits are more, number of bits are more, how much communication do we expect? Suppose the number
No,
is
no. I can just put them. I can just specify the bit positions. I have explained already the code for that, right, ma'am. Whatever the output comes, that I can convey to the sender through public channel. Not only phone. I'm saying just even they can communicate over phone. Also, nothing will happen. I'm saying, ma'am.
Okay.
Ma'am,
No, suppose I am
I'm saying
sending it
that
via, I am sending it via other means. Suppose if it is phone, if they don't understand, they can call it and these people will repeat. But what
generally
if
it
I
will be
am sending
automated,
via
ma'am. Once
another
the key
channel?
is generated, so these positions will be shared with the allies automatically through one programming, the automated programming. But what I'm saying is generally to tease the eavesdropper. So we are openly challenging the eavesdropper. Even if I call through phone and if it is recorded, even if you tell to the eavesdropper what are the positions, he cannot crack it. I'm saying.
So if I send the key and the key gets garbled, this is what you are saying, no? First 50% of the bits to be verified.
Yeah, if first 50% of the bits are verified by, that means these first 50% bits are first 50% of the bits also can be transmitted through the channel, insecure channel. Nothing will happen because other 50% is safe. According to the no cloning theorem, what they are saying that it is not that easy to crack the remaining 50% also.
Tracking is okay, but what if they are garbled during the transmission?
That is the problem. That is the problem with the quantum cryptography. That will be the problem.
Okay. Okay,
That we have to modernized algorithms have to come. Everything has to be versions have to be improved now.
Okay,
So
sir.
all these experiments we can do once the complete quantum machinery comes into picture and what is happening, then only we can answer all these questions.
Correct, sir. So strongly to vouch on these things, maybe we need the practicality of quantum computing.
Yeah, all these are assumptions. Whatever we are currently doing, all these things are just constructing all the buildings in the air.
All are assumptions only as of now.
Yes, sir. Understood.
Yes.
Thank you.
That's why majority of the professors also, whenever they are explaining quantum, so first they will put that whatever we are listening is whatever you are listening is an assumption.
Hello, sir. I have a
Huh, ma'am.
question, sir.
Huh, ma'am.
It's a general question, like basically for implement that practically quantum computers to come into existence, we require a cryogenic environment that is most important to maintain coherency.
Yes, yes, ma'am.
How far it is possible for us to bring on practically? Are there anything research going on to bring on computers where you don't have this noise
Uh,
or this
that we cannot say,
temperature?
ma'am. See, whenever we are in 2010, we don't have even proper touch phone.
Yes, sir.
Now the scenario is such a way that we may have the palm phones in future. That means without any device, we can speak to a person, or with that virtual reality may come into picture, and we can speak to a particular person, even if the existence of the person is not there. And with this chat GPT, we are seeing a lot many wonders. Previously, if you want to write any paper, we have to sit and read do the literature, and we have to do all these works. But nowadays, if anyone want to write a paper, they can write in one day also. If there is no AI plagiarism is considered, if AI plagiarism is considered for the publication, so that we cannot expect from what anything may happen in future.
Oh, okay, sir. Sir, one more question, sir. Like even in a previous one of the session, I came to know about this quantum tunneling. Where is tunneling actually in use in quantum computers? I have not come across anywhere in this sessions. Any idea, sir?
Sorry, ma'am. Something you are asking. Sorry.
Sir, I just want to know where quantum tunneling is exactly used in quantum computers.
As of now, that kind of research I didn't do.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Ma'am, thank you, Sita Commissioner. Ma'am, thanks for giving this opportunity to deliver
Thank you,
session.
sir. Thank you so much, Dr. Vishnu, sir, for the insightful session. So in
Yes,
this
ma'am.
very interesting session, we
Sorry,
have
ma'am, that
learned.
in intro at the time of intro I didn't see properly, so I
Once
I
again,
was
I
in
will
that
introduce
concepts and
myself.
all those things.
I am Dr. C.H. Sita Kameswari, Associate Professor, Department of CSC A&ML, KMIT. Now you
Thank you,
can
thank you.
recognize, sir.
No, not required, ma'am. Now I can after seeing the name only I got doubt. So
Okay. So in today's interesting session, we have learned many concepts such as mainly what is post-quantum cryptography and regarding quantum computing risk, current security levels, and PQC hybrid approaches for TLS. And also we have gained knowledge on practical implementation of RSA key generation. So on behalf of organizing committee of FPP and KMIT, I express my sincere gratitude for taking your valuable time to share your expertise with us, sir. Your presentation is informative and the insights you provided are valuable. Once again, thank you so much, sir.
Thank you so much, ma'am, for giving opportunity to deliver a session at KMIT.
So nice to see you after a very long time. I think almost after 15, 20 years.
Yes, ma'am. After ANITS, I left ANITS in 2012, ma'am.
Yeah, even myself.
After that,
I also left
yeah.
in 2012.
Yes. I went to Geetham and you went to Hyderabad, I think.
Ha.
Thank you so much, ma'am.
Thank you, sir.
Thank you, Kishore sir, for giving this opportunity. Thanks for inviting me. Kishore sir was my BTech senior.
Yeah.
Thank you. Thank you, Vishnu sir. Okay.
He was my super senior, not even senior.
Okay.
Yes,
Madam, continue, madam. Vishnu
So
sir, thank you so much, sir.
Thank
Sita
you,
madam.
sir.